let's talk about improper integrals. This will be specifically what we're calling type 1, which is the kind that has infinity as one or both of the bounds. So you can see the example that we're going to do in this video. So we have the integral from 1 to infinity of 1 over x squared dx. And we're answering two questions that kind of come as a package deal here. So the first question is this integral convergent or divergent? Which also means, does it converge or diverge? We kind of use those words both ways. And then the follow-up is, if it's convergent, find its exact value. Okay, so I want to start by just kind of thinking about what is going on here, what makes this an improper integral, and then we'll work through the steps of actually computing something like this very carefully. Okay, so what I have on the side here is a sketch of the graph of 1 over x squared. We only care about from 1 to infinity, so we only care about kind of this piece of it. There's more over here. So if we're integrating from 1 to infinity, we would start at 1, and then you don't actually have like a stopping x value on the right-hand side. You just kind of integrate the area forever here. So this is a horizontal asymptote, so this graph is getting super close to the x-axis, but we'll never actually touch it. So there's like this teeny little bit of red area that goes on forever in that direction. So sometimes when you do an integral of what is essentially an infinite, 2D space here, sometimes you'll get that it really does just add up to infinity, right? Like it's infinite area, it's literally infinite magnitude. And then sometimes you actually get that it equals an exact number, and that would be the convergent case, right? So convergent or divergent would mean it actually equals a number, which is why they're asking for it, or it's probably equal to infinity. Sometimes divergent can also mean like it oscillates and goes crazy, but we'll kind of see the part in the work where you can make the decision between these two. Okay, so the reason that this is an improper integral is because this upper bound is infinity, and that means that we can't just compute this the way that we would a normal definite integral with two numbers, because once you do the antiderivative, you'd have to plug in the bounds, and infinity isn't a number. It's kind of a concept more than a number. So it's not something we can directly plug in, but it is something where we can kind of think about the limit of the function as you get closer to that upper bound. So what we're going to do every time we have an improper integral is kind of identify where the problem is, and for this one clearly it's the infinity. So what we will do instead is rewrite this integral. I'm going to have everything the same here, and instead of actually having an infinity there, right, because we said like technically the definite integral doesn't exist that way, we're going to put some letter up here and then limit that letter to infinity. So I usually choose A if it's the bottom to negative infinity, or B if it's the top, but really that choice of B, it could be any letter that's not X, because X is already being used. Okay, so what we're going to do for the next several steps here is just attempt to compute what this is, and if the limit exists, then we'll say convergent, here's my number. If the limit doesn't exist when the time comes, then we'll say it's divergent, and that's your whole answer. So for now, we just kind of ignore this limit. It comes down in every step for as long as we can ignore it, essentially. So I'm going to go one more step here and just rewrite my integrand as x to the negative 2, because to integrate 1 over x squared, I want to use the power rule, so I want to see it in this format. X to the negative 2 will integrate to 1 over negative 2 plus 1, x to the negative 2 plus 1, and that simplifies to negative 1 over x. This is my antiderivative of this function here. So that limit notation carries down again. I'm not doing anything with it. I'm going to put the antiderivative of this function here. So essentially I'm just carrying down the limit and just computing this definite integral. It just happens to have an upper bound. That's a mystery. So my antiderivative is negative 1 over x, and that's being evaluated from 1 to b. I'm using this vertical bar notation here to keep track of the upper and lower bounds. But I no longer have the integral, right, because I actually did the antiderivative, so I can't use integral dx anymore. So this is like my intermediate step where I just keep track of them. Okay, so I would say this out loud. Negative 1 over x evaluated between b and 1. So I'll plug in b for x, plug in 1 for x, and subtract between the two. And we still have that limit notation on the outside. So this is with a b in there, minus with a 1 in there. All right. So we could at some point acknowledge that this becomes a plus 1, right? So a negative makes you positive, and then this just simplifies to 1. So what we're really concerned with now is the limit, right? We've pretty much gone as far as we can ignoring that limit. Now we have to decide what this is. The limit as b approaches infinity of the expression negative 1 over b. Now, if this limit exists, we're going to say convergent, and then we'll come up with a number. If this limit doesn't exist, we'll say divergent, and that's the end of the problem. I'm pausing so that you can think about it. So this limit does exist. Negative 1 divided by bigger numbers will eventually head towards 0. So this limit equals 0. So because that limit exists, I'm going to say convergent. I can tell that right away. And then now we have to answer the follow-up question, right? If it's convergent, compute the exact value here. So we'll say, okay, this came out to 0, and then the rest of this was plus 1. So altogether, this comes out to just the number 1. So this integral is convergent, and it turns out that this infinite red space here has area exactly 1. So every improper integral, even of this type where one of the bounds is infinity, they all have the same steps, but they'll kind of go different ways depending on what your function is, what the range is. But generally what stays the same for an improper integral is you want to identify which of your bounds is the issue, in this case it's the infinity, put a letter in that spot, limit the letter to the infinity. Then that limit kind of carries down the next several steps as you just kind of go about your business doing your definite integral, right? So we just did our antiderivative, plugged in the two bounds. Then we needed to decide about this limit. If it exists, you say convergent. If that limit doesn't exist, you say divergent. And if it's convergent, you can keep going and finish off to the final number.